All right, so we want to look at the chi-square test of independence. Tests of independence are going to use a contingency table that has the observed data values, and then the test statistic for the test of independence is similar to that of the goodness of fit test. It's just this guy down here that's going to be different. So O is still the observed values, E is still the expected values. I is going to be the number of rows in your table. J is going to be the number of columns in your table. And the test of independence is exactly that. It wants to figure out whether the two things that you're working with are independent or are they not. So a few things about this. The expected value for each cell has to be at least 5 in order for you to use this. We're going back to some probability with this. If A and B are independent, then remember that the probability of A and B will be the same thing as the probability of A times the probability of B. In a test of independence, we're again going to state the null and alternate hypothesis. And since the contingency table has two factors, the null hypothesis is always going to be that those factors are independent. The alternate hypothesis is always going to be that those two things are not independent, that they're dependent. So you don't even have to think about it. That's a given for your null and alternate. The test of independence is always right-tailed as well. So the number of degrees of freedom for the test is a little bit different. It's going to be the number of columns minus 1 times the number of rows minus 1. Now, remember, columns go up and down, rows go across. So think about like architecture downtown. Columns in front of like churches and buildings go up and down. If you go to a concert and you're sitting on a particular row, that goes across. So here's how we can figure out our expected number E. We're going to take the total of the row. So basically we're going to add all the values up in the row, multiply it by the total of the column. We're going to add all the values up in that column, and then divide it by the total number surveyed. Okay, so let's look at an example. In a volunteer group, adults 21 and older volunteering from 1 to 9 hours each week to spend time with a disabled senior citizen. The program recruits among community college students, four-year college students, and non-students. In the table is a sample of the adult volunteers and the number of hours that they volunteer per week. So we want to figure out, is the number of hours volunteered independent of the type of volunteer? Okay, so like we said, the null hypothesis is always going to be the two things are independent. The alternate hypothesis is always going to be that the two things are dependent. So that's a no-brainer. I don't have to think about it. And we also said that it's always going to be right-tailed. So here's that observed table that they gave us. How are we going to come up with that expected value? Okay, so here was the formula that they gave us to find the expected value. They said take the row total, multiply it by the column total, and divide it by the total number surveyed. Okay, so let's look at this first one right here, the one that's in the spot of 1 to 3 hours for community college students. Okay, so if I come up here, my row total is going to be right here, 255, right? Because this is my row, and you can see right over here, here's the row total. They added up 111, 96, and 48, and they got 255. All right, so there's the row total. Then I'm going to multiply that by the column total. Okay, so again, this is the column. So if I come up here, that would be 111 plus 96 plus 91. That would be 298. So that's where we're getting this guy. And then we're going to divide that by the total number in the survey. So you can see that right over here. And if you had added the row totals or the column totals, you would have gotten that. All right, so we're going to divide that, and that's where we're getting this 90.57. All right, so go ahead and pause the video if you would, please, and calculate the values that are not already filled in for you on the table to make sure that you can do them correctly. And then you can unpause the video to check them and make sure you got them right. Okay, so here are the values that you should have gotten. I filled in most of them for you, but like for this guy right here, for this 115.19, we took the row total 255 times the column total 379 and divided it by 839. For this guy right here, we took the row total 255 times the column total 162 and divided it by 839. And then again, these were already filled in for you, but like for this one, we took the row total, which was 294, times the column total, which was 298, and divided it by the overall total, which was 839. Okay, so this is how we got our expected table. So now we have an observed table and an expected table, and I need to multiply those. And the way that I'm going to multiply those fast and easy on my calculator, because it is miserable otherwise, is I'm going to use matrices. Because remember, matrices gave us a way that we could organize basically spreadsheets, right? Like things that had rows and columns in them. So let me remind you of how you're going to do this. First off, we're going to put these values in matrix A, and we're going to put these values in matrix A. Matrix B, sorry. So let me show you how we're going to do that. All right, so on your calculator, you're going to go to matrix, and you're going to go over to edit and choose matrix A. And you can tell it whatever you want. So if it doesn't already say 3 by 3, no problem. As soon as you type 3, enter, 3, enter, it'll lay out a 3 by 3 for you. And these are going to be our observed values. I'll call them out to you. So 111, enter, 96, enter, 48, enter, 96, 133, 61, 91, 150, 53. Okay, now second quit out of that. Go back to matrix again and go over to edit again. And this time I'm going to go to matrix B. So you can see I've scrolled down to matrix B and I'm sitting on edit. So I'm going to hit enter. And again, I'm going to tell it 3, enter, 3, enter. And now I'm going to put those expected values in that we calculated. So let me call them out to you again. So 90.572, enter. 115.19, 49.237, 103, 131, 55.995, 104.42, 132.81, 56.768. Okay, so now that I've got those in there, I'm going to go back to the PowerPoint to make it a little bit easier for you to see what we're doing. All right, so again, just to review, we went to matrix, we went over to edit, we chose matrix A, we told it we wanted a 3 by 3, and we put in the values that we had over here from the observed, right? Then we did second quit to get out of that. We went back to matrix, we went over to edit and went down to matrix B, and again chose a 3 by 3, and we put in these values that were from our expected table. So these were our expected values, and then I'm going to second quit out of that. Okay, so now I'm going to go to statistics, not distribution, not like what we did last time. I'm going to go to statistics, and I'm going to arrow over to tests. It's the same place that we've got like our 1 prop Z and that kind of stuff. I'm going to go down to the chi-squared test right here. All right, and when I do that, for observed, I'm going to tell it matrix A. Okay, so here's how I tell it matrix A. So I'm going to go back to matrix, and I'm going to stay right here on names, and I'm going to choose A and hit enter. When I want to tell it matrix B, I'm going to go second matrix, and I'm going to stay right here on names, and I'm going to go down here to B and hit enter. All right. So that's how I tell it to put in the A that you see right here and the B that you see right here. Okay, then you can either ask it to calculate it or draw it. Either one. I did both. So here's the drawing. And then here's our calculation. So here's our chi-squared test statistic, 12.9909. And here's our P, 0.01132. Now, notice nowhere did they ask me for the degree of freedom in here. They computed that for me. So you don't have to calculate the degree of freedom. They'll figure that out for you if you want them to. Okay, so we calculated the test statistic. We got 12.99. Here's the notation that we're going to use for that. And as we just said, you could compute the degrees of freedom on your own, but the calculator had just already found it for us, right? So we don't have to. If they ask you to graph it, we just saw on the calculator how you could graph that as well. And basically what we're looking for, we had found our p-value was 0.0113. And again, we're going to do what we've been doing. We're going to compare alpha and p. Now, if no alpha is given, we've always said that we would do a 95% confidence level. So a level of significance of 0.05, and that's the same case here. If it's not given, then assume 0.05. So you'll notice that alpha is greater than p, or p is less than alpha. So in that case, we reject the null hypothesis. Now, the null hypothesis was that these were independent, right? So if we reject that, then that means that the factors are not independent. So the way that we would sum that up is we would say, at a 5% level of significance from the data, there is sufficient evidence to conclude that the number of hours volunteered and the type of volunteers are dependent on one another. They're not independent, they are dependent. Okay, so we've looked at two different types of chi-squared tests. There are actually three, but we're only looking at two. So the first one was the goodness of fit test, and the second one was the independence test. And I just tried to sum them up here for you with information about both so that you could see the similarities and the differences. Okay, because I am out sick right now, the only thing that I'm going to ask you to do on homework, quiz, lab, test is the goodness of fit test. I'm not going to ask you to do the test for independence with all the matrices and all of that kind of stuff because I know that that's a lot more challenging. All right.